Hey everybody, it's First Warn Storm Team Chief Meteorologist Brad Petovich. Welcome to WCNC's Weather School for May 21st. We're talking about something you've heard probably quite often on TV, online. You probably even a little bit familiar with the term weather models, but a lot of folks don't understand what they are, how they work, and really in some cases how they don't work. I think a lot of people think a model is a forecast, and it's not. And what a model is, we in the meteorology community actually refer to them in a couple different ways. We refer to them either as numerical weather prediction, which tells you there's a lot of numbers involved, a lot of math. This is the math part of meteorology that people sometimes don't really get a grasp of until they get into meteorology, is that modeling is essentially a giant math problem. The other term we use is guidance, numerical guidance. And the key part is guidance. For us, they're tools to build a forecast, not an actual forecast. The other term we often refer to is gridded data. And I'm going to explain why those terms are used. And when you see how models work, you might actually get a little understanding of why we use those type of terms. So first thing you got to understand about modeling the atmosphere, there are a lot of inputs. So you need a lot of data to go in. Now, where does that data come from? Well, I'll show you where the collection of that data comes from in a second, but we've got to take into account a lot of things in the atmosphere. Incoming solar radiation, radiation from the atmosphere, from the ground, from the sun, evaporation between the ocean and water and the atmosphere, heat exchange, radiation from the earth, topography, which is mountains or hills or trees or even buildings, formation of rain, snow, ice. There's a lot of parameters. All these energy budgets and heat fluxes are really important. So how do we count, or how do we actually collect that data? Well, this is the important part of meteorology. We can't really run a model unless we have a bunch of data in it. And a good way to think about a model is that it's a calculation or a word problem that needs numbers to go into it. Where do those numbers come from? Well, in this case, we collect a ton of data, and some might not even realize how much data we collect. We collect data from satellites, from weather balloons, from ground sensors, your basic weather station that you've heard us talk about, radar, ships, buoys. But one thing that's really important, and it's been important during this pandemic, is aircraft data. In fact, every airplane that takes off and lands across the entire world collects weather data from the moment it takes off to the moment it lands and as it flies. So temperatures at certain altitudes, wind speeds, direction, pressure, dew points, that information is vital. And actually, during the pandemic, we've lost like 80% of that aircraft data that goes into the modeling. So that's a pretty big difference. Now, I don't know how much it's impacting the models. I haven't noticed a huge change, but it's pretty significant, the number of aircraft data missing that we actually would love to have right now. Also, we collect a ton of data from trucks now. Some trucks driving delivery trucks collect weather data, and more phones are collecting weather data from us, barometric pressure, temperature, and other things that go into the modeling. So why is a model sometimes referred to as a gridded data? You may have heard me say that. Well, to understand that, you got to look at this image here, which I hope this is a better one. So the way we simulate the atmosphere is we break up the atmosphere into a grid. Think of grid paper. If you ever had that, we actually are trying to calculate points on the grid, but it's just not a flat grid at the surface. These grids go up in the atmosphere. There's layers, because remember, we just don't, even though weather happens down where we are, what's going on the jet stream level, the mid levels, and the top of the atmosphere is really important to what happens down here. We also run this grid or model in the ocean to a depth, because like for hurricane season, we need to know how deep the warm water is. We need to know the currents in the ocean. So this is a really complex setup. When you look at this graphic, I think is really useful as well. It kind of shows you the boxes that we're building. And depending on the models, some models have 12, 15, 25 layers or grids, or they might have less. Now, the grid domain we refer to as like how closely the grids are, like is it a big box or little box, is how to refer to as resolution. So high resolution models have a ton of boxes, and small resolution or poor resolution models have big boxes. So let me kind of give you an example of what this looks like on a grid. I saw this blog post the other day, and it really is a good example of what's going on here. If you look carefully on your screen, we're trying to forecast those grid points. So the model is basically forecasting a point on the grid. But what the computer does, or the model does, is it extrapolates the difference and fills in the gaps. This is where modeling can be a problem, and why you can't always look at modeling as an actual forecast, because it's not actually forecasting every single spot on Earth. It's forecasting on those grid points. Now, those grid points could be 12 kilometers across or 9 kilometers across. So in between, the model is basically assuming certain things are happening. And how this becomes problematic, and actually what I'm going to do is add. So you can see the grid is trying to forecast that point, and that point. But in between, it has to draw a line, like connecting the dots. And that's kind of up into interpretation of the model. So why does this become a problem for forecasters when we're trying to generate a forecast? Well, this is a great example. On the right is a model forecast of what they think the thunderstorm is going to look like. And on the left is actually what it looks like on the radar. If you look carefully, the grid points on the right, model's trying to pick that there's a big cell there, so it just starts filling in the gaps with giant amount of rain, when in reality, the heaviest rain is right there. This has a lot to do with the resolution of the model and why you have to understand how the modeling works for you to have a really good understanding of what, how you're going to put a forecast together. So let me show you some cool examples of what modeling can look like. This is actually a model of what the wind is doing right now across the world. Another view of it is here. So obviously we're not collecting data in real time in every single spot around the world, but what's cool about this is that we're actually able to simulate it pretty accurately. Now, like a video game, if you've ever played a video game, if you play Minecraft, or for a lot of us, if we play sporting games or other games on Xbox or PlayStation, one of the things that is it's a simulated world. And when you interact with that simulated world, you change the outcome. And that's where, as a meteorologist, we come in and figure out how the interactions are going to change the outcome of the simulation. So let me show you some of the model data. This is actually real-time data. What I'm going to show you is what I normally do on a given day is I look at all these different, look at all the different models I can look at right now. I've got a ton of them. So for instance, one of the models I may look at would be the European model, which you probably have heard quite a bit. I pick a domain, the United States. I have maps of looking at, I want to look at North Carolina. So I'll scroll down here and I find North Carolina, and then look at all the parameters of the model. A lot of times you might see online a snowfall map or a temperature map. Those are just simplified model maps. We basically have hundreds of different versions to look at. So from clouds to moisture to relative humidity. One of my favorites is the cloud layers. Oops, I got to log in here. Go back to the city chart here. So I'll pick my model again, United States. We'll go to North Carolina. And one of my favorite charts is this chart right here, the cloud layer chart. And if you look, it shows you the different clouds at different layers in the atmosphere. So it's really cool to kind of see how the simulation works out. And one of the things as a meteorologist that we often have to do is, as I mentioned, this is guidance. These are not forecasts. So when you see like the spaghetti plots for a hurricane, or you see a snowfall map, they're always wrong. And you're probably saying, what? Yeah, we have a saying, all modeling is wrong, but some models are useful. What you need to know is a model is not trying to forecast a specific amount of snow or a specific amount of rain or a specific temperature. Even though it's giving you that information, what it's really trying to do is give you a range of possibilities. So we're looking for that range, and we're trying to find the most likely scenario in that range. And that's where the skill as a forecaster and meteorologist comes in. These are the tools we are using to build a forecast. A good way to look at this is like building a house or building a table. If you're a carpenter, you have wood, nails, glue, saws, measuring tape, sandpaper. Those are the tools. They don't build the table themselves. You need to build the table. So that's where the skill as a meteorologist or a carpenter comes in, and using these tools to put a forecast together. And just because you look at these tools doesn't always mean you're able to put a forecast together. Like I think I'm pretty handy. I can go to Home Depot or Lowe's and buy just about anything, but it doesn't mean I can build anything. I can buy the tools, but I always can't build the product. So that's what we do as meteorologists, to try to forecast what's going to happen in the atmosphere. And it's really cool, the simulations we can run now. And as these models get better and better, the data gets better and better, our forecasts get better. As the tools become better, we're much more able to really take a look at what's going on in the atmosphere. So I hope you enjoyed today's weather school. We'll be talking more about weather tomorrow at 1 o'clock here on WCNC's Weather School. Just a really cool fascination with weather and meteorology. If you like science, you would love modeling, but I will caution you, this is the biggest math part about our job. All these calculations are math problems. So if you're really good at math, a lot of people go into modeling of the atmosphere more than forecasting, but you got to have a grasp and understanding how they work. So thanks for tuning in to today's Weather School. If you miss any of these episodes or you have questions, please hit me up, WXBrad on Twitter, Facebook, and Instagram. And you can see all our past episodes on WCNC.com or our WCNC YouTube channel. We have a whole playlist with all of our Weather School episodes. Hope you have a great day, everybody. We'll be back here tomorrow at 1 o'clock for WCNC.